name is Hello guys, my name is Dixita and today I give you some learnings from the DBMS subject. And this point is data model schema and instance. The data which is stored in the database at a particular moment of time is called an instance of the database. The overall design of a database is called schema. A database schema is the skeleton structure of the database. It represents the logical view of the entire databases. A schema contains schema, object like table, foreign key, primary key, views, columns, data types, stored procedure, etc. A database schema can be represented by using the visual diagram. That diagram shows the database objects and relationship with each other. A database schema is designed by the database designers to help programmers whose software will interact with the database. The process of database creation is called data modeling. A schema diagram can display only some aspect of a schema like the name of record type, data type, and constraints. Other aspects can't specify through the schema diagram. For example, the given figure neither show the data type for each data item nor the relationship among various files. In the database, actual data changes quite frequently. For example, in the given figure, the database changes whenever we add a new grade or add a student. The data at a particular moment of time is called the instance of the database. Next point is DBMS data independence. Data independence can be explained using the three schema architecture. Data independence refers characteristic of being able to modify the schema at one level of the database system without altering the schema at the next higher level. There are two types of data independence. First is logical data independence. Logical data independence refers characteristics of being able to change the conceptual schema without having to change the external schema. Logical data independence is used to separate the external level from the conceptual view. If we do any changes in the conceptual view of the data, then the user view of the data would not be affected. Logical data independence occurs at the user interfaces level. Second is physical data independence. Physical data independence can be defined as the capacity to change the internal schema without having to change the conceptual schema. If we do any changes in the storage size of the database system server, then the conceptual structure of the database will not be affected. Physical data independence is used to separate conceptual levels from the internal levels. Physical data independence occurs at the logical interfaces level. Database language in DBMS. A DBMS has appropriate language and interfaces to express database queries and updates. Database language can be used to read, store, and update the data in the database. Types of database language. Data definition language means DDL. DDL stands for data definition language. It is used to define database structure or pattern. It is used to create schema, table indexes, constraints, etc. in the database. Using the DDL statements, you can create a skeleton of the database. Data definition languages is used to store the information of metadata like the number of tables and schemas, their names, indexes, columns in each tables, constraints, etc. Here are some tasks that commonly DDL create. It is used to create objects in the database. Alter. It is used to alter the structure of the database. Drop. It is used to delete objects from the database. Truncate means it is used to remove all records from a table. Rename. It is used to rename an object. Comment. It is used to comment on the data dictionary. These commands are used to update the database schema. That's why they come under data definition language. Second is data manipulation language, means DML. DML stands for data manipulation language. It is used for accessing and manipulating data in a database. It handles user request. Select. It is used to retrieve data from a database. Insert. It is used to insert data into a table. Update. It is used to update existing data within a table. Delete. It is used to delete all records from a table. Merge. It performs upsert operations. Therefore, insert or update operations. Call. It is used to call a structured query language or a Java subprogram. Explain plan. It has the parameter of explaining data. Block table. It controls concurrency. Third is data control languages, means DCL. DCL stands for data control language. It is used to retrieve the stored or saved data. The DCL execution is transactional. It also has rollback parameters. But in Oracle database, the execution of data control language does not have the feature of rolling back. Here are some tasks that come under DCL. Grant. It is used to give user access privileges to a database. Revoke. It is used to take back permissions from the user. There are the following operations which have the authorization of revoke. Connect, insert, usage, execute, delete, update and select. Fourth is transaction control language, means TCL. TCL is used to run the change made by the DMS statement. TCL can be grouped into a logical transaction. Here are some tasks that come under TCL. Commit. It is used to save the transaction on the database. Rollback. It is used to restore the database to original since the last commit. Next is access properties in DBMS. DBMS is the management of data that should remain interchanged when any changes are done in it. It is because if the integrity of the data is affected, all data will get disturbed and corrupted. Therefore, to maintain the integrity of data, there are 4 properties described in the database management system, which are known as the asset properties. The asset properties are meant for the transaction that goes through a different group of tasks, and there we came to see the role of the asset properties. In this section, we will learn and understand about the asset property. We will learn what this property stands for that and what does each property is used for. We will also understand and the asset properties with the help of some examples. Asset properties means atomicity, consistency, isolation, durability. Atomicity. The term is atomicity defines that the data remains atomic. It means if any operations is performed on the data, either it should be performed or executed completely or should not be executed at all. It further means that the operation should not break in between or execute partially. In the case of executing operations on the transaction, that operation should be completely executed and not partial. Example: if Remo has account having $30 in his account, from which he wished to send $10 to Shiro's account, which is B. In account B, a sum of $100 is already present. When $10 will be transformed to account B, the sum will become $110 now. There will be 2 operations that will take place. One is the amount of $10 that Remo wants to transfer will be debited from his account A, and the same amount will get credited to account B. Therefore, into Shiro's account now, what happens? The first operation of debit executes successfully, but the credit operations, however, fails. Thus, in Remo's account A, the value becomes $20, and to that of Shiro's account, it remains $100 as it was previously present. In the above diagram, it can be seen that after crediting $10, the amount is still $100 in account B, so it is not an atomic transaction. The below image shows that both debit and credit operations are done successfully. Thus, the transaction is atomic. Thus, when the amount loses atomicity then is in the bank system, this becomes a huge issue and So the atomicity is the main focus in the bank system. Consistency. The word consistency means that the value should remain preserved always in DBMS. The integrity of the data should be maintained, which means if a change in the database is made, it should remain preserved always. In the case of transaction, the integrity of the data is very essential so that the database remains consistent before and after the transaction. The data should always be correct. In the above figure, there are three accounts A, B, and C, where A is making a transaction T one by one to both B and C. There are two operations that take place. Therefore, debit and credit. Account A firstly debit $50 to account B, and the account amount in account A is ready $300 by B before the transaction. After the successful transaction T, the available amount in B become $150 now. Now debit $20 to account C, and the debit and credit operation from account A to C has been done successfully. We can see that the transaction is done successfully and the value is also read correctly. Thus the data is consistent. In case the value read by B and C is $300, which means that data is inconsistent because when the debit operation execute it will not be consistent. Third is isolation. The term isolation means separation. In DBMS, isolation is the property of a database where no data should affect the other one and may occur concurrently. In short, the operation on one database should begin when the operation on the first database gets complete. It means if two operations are being performed on two different databases, they may not affect the value of one another. In the case of transactions when two or more transactions occur simultaneously, the consistency should remain maintained. Any changes that occurs in any particular transaction will not be seen by other transaction until the change is not committed in the memory. This example is if two operations are concurrently running on two different accounts, then the value of both accounts should not get affected. The value should remain persistent. As you can see in the below diagram, account A is making T1 and T2 transaction to account B and C, but both are executing independently without affecting each other. It is known as isolation. Fourth is durability. Durability ensures the permanency of something. In DBMS, the term durability ensures that the data after the successful execution of the operation become permanent in the database. The durability of the data should be so perfect that even if the system fails or leads to a crash, the database still survives. However, if it gets lost, it becomes the responsibility of the recovery manager for ensuring the durability of the database. For coming the values, the commit command must be used every time we make changes. Therefore, the ACID properties of DBMS plays a vital role in maintaining the consistency and availability of data in the database. Thus, it was a precise introduction of ACID properties in DBMS. We have discussed these properties in the transaction section also. Next topic is ER means entity relationship diagram in DBMS. ER model stands for an entity relationship model. It is a high-level data model. This model is used to define the data elements and relationship for a specified system. It develops a conceptual design for the database. It also develops a very simple and easy to design view of data. In ER modeling, the database structure is portrayed as a diagram called an entity relationship diagram. ER model stands for an entity relationship model. It is a high-level data model. This model is used to define the data elements and relationships for a specified system. It develops a conceptual design for the database. It also develops a very simple and easy to design view of data. It develops a conceptual design for the database. It also develops a very simple and easy to design view of data. In ER modeling, the database structure is portrayed as a diagram called an entity relationship diagram. For example, suppose we design a school database. In this database, the student will be an entity with attributes like address, name, ID, age, etc. The address can be another entity with attributes like city, street name, pin code, etc. And there will be a relationship between them. First is entity. What is entity? An entity may be any object, class, person, or place. In the ER diagram, an entity can be represented as a rectangle. Consider an organization as an example. Manager, product, employee, department, etc. can be taken as an entity. Entity means employee, and then work for means relation is work for the department. Employee relation is department for the work. And the first point is weak entity. Weak entity means an entity that depends on another entity called a weak entity. Weak entity means one possible events are dependent on another entity, means another department info, another entity dependence in another entity. The weak entity doesn't contain any key attribute of its own. The weak entity is represented by a double rectangle. When entity is represented in rectangle and so that a weak entity is represented in double rectangle. Second is attribute. The attribute is used to describe the property of an entity. Ellipse. Ellipse is used to represent an attribute. For example, ID, age, contact, number, name, etc. can be attribute of a student. Yes. And then first is key attribute. Key attribute means the key attribute is used to represent the main characteristic of an entity. It represents a primary key. The key attribute is represented by an ellipse with the text underlined. Second is composite attribute. An attribute that composed of many other attributes is known as the composite attribute. The composite attribute is represented by an ellipse, and those ellipses are connected with an ellipse. Third is multi-level attribute. Multi-valued attribute. An attribute can have more than one value. These attributes are known as multi-valued attribute. The double oval is used to represent multi-valued attribute. For example, a student can have more than one phone number. Derived attribute. An attribute that can be derived from other attribute is known as the derived attribute. It can be represented by a dashed ellipse. For example, a person's age changes over time and can be derived from another attribute like date of birth. Relationship. A relationship is used to describe the relationship between entities. Diamond or rhombus is used to represent the relationship. Teacher relation is student. Then teacher relation is teaches is the relation, and then teaches is will also represent in recto diamond shape. Then relationship has been represented by in diamond shape. Types of relationships are as follows. One-to-one relationship means when only one instance of an entity is associated with the relationship, then it is known as one-to-one relationship. For example, a female can marry to one male, and a male can marry to one female. Then 1 to 1 female married to male. This is female and this is male. Then married to male. This is 1 to 1 relationship. Married to is a relation. Relationship means representing a triangle shape. Those, therefore, female is entity. Then represent in rectangle. Then married male is also entity. This is also represent in rectangle shape. And therefore, female married to male. Married to means relationship. Relationship represent two diamond shape. Second point is one to many relationship. When only one instance of the entity on the left and more than one instance of an entity on the right associates with the relationship, then this is known as one to many relationship. For example, scientists can invest many inventions, but the invention is done by the only specific scientist and then invention. Scientists invest in invention. This is one to many means scientist one and invention is one or one than more than one. Scientist invest is the invention and scientist between the relation in invents many to one relationship. When more than one instance of the entity on the left and only one instance of an entity on the right association with the relationship, then it is also known as the many to one relationship. Therefore, above you look, the relationship is one to many. And then next topic is many to one, means this is above example is flip in horizontal. And then for example, for the student enrolls for many only one course, but a course can have many students, means students is one or more than one, and then course is one, and then students study in one course. This means more than one student, and course is designed in web development course. 5 students are interested on a web development course, and then this example very perfect for the many to one relationship manner. Many to many relationship. When more than one instance of the entity on the left and more than one instance of entity on the right associates with the relationship, then it is known as many to many relationship. For example, employees can assign by many projects and projects can have many employees. This example is many employees means more than one person, more than one employees, and then projects are very more than one, and then employees are work on more than one project, and projects are given by more than one employees. Therefore, this example is related on many to many relationship. Next topic is notation of ER model. Database can be represented using the notation in ER model. Database can be represented using the notation. In ER diagram, many notations are used to express the cardinality. These notations are as follows. Next point is cardinality in DBMS, means mapping constraint. DBMS stands for Database Management System, which is a tool or a software used to do various operations on a database like the creation of the database, deletion of the database, or updating the current database. To simplify processing and data querying, the most popular types of databases. Currently in use, typically model their data as row and columns in a set of tables. The data may then be handled, updated, regulated, and structured with easy. For writing and querying data, most databases employ structured query language, means SQL. Next point is cardinality. Cardinality means how the entities are arranged to each other, or what is the relationship structure between entities in a relationship set in a database management system. Cardinality represents a number that denotes how many times an entity is participating with another entity in a relationship set. The cardinality of DBMS is a very important attribute in representing the structure of a database. In a table, the number of rows or tuple represent the cardinality. Cardinality ratio. Cardinality ratio is also called cardinality mapping, which represents the mapping of one entity set to another entity set in a relationship set. We generally take the example of a binary relationship set where two entities are mapping to each other. Cardinality is very important in the database of various business. For example, if we want to track the purchase history of each customer, then we can use the one-to-many cardinality to find the data of a specific customer. The cardinality model can be used in database by database managers for a variety of purposes, but corporations often use it to evaluate customer or inventory data. One to one. Second is many to one. Third is one to many. Fourth is many to many. One to one means one to one cardinality is represented by 1:1 symbol. In this, there is at most one relationship from one entity to another entity. There are a lot of examples of one-to-one cardinality in real life databases. For example, one student can have only one student ID, and one student ID can belong to only one student. So the relationship mapping between student and student ID will be one-to-one cardinality mapping. Another example is the relationship between the director of the school and the school, because one school can have a maximum of one director and one director can belong to only one school. Many to one cardinality. In many to one cardinality mapping from set 1, there can be multiple sets that can make relationship with a single entity of set 2, or we can also describe it as from set 2 and one entity can make a relationship with more than one entity of set 1. One-to-one cardinality is the subset of many-to-one cardinality. It can be represented by many to one, means more than one, then ratio 1. For example, there are multiple patients in a hospital who are served by a single doctor. So, the relationship between patient and doctors can be represented by many to one cardinality. One-to-many cardinalities. In one-to-many cardinality mapping from set 1, there can be a maximum single set, then can be a relationship with a single or more than one entity of set 2. Or we can also describe it as from set 2, more than one entity can make a relationship with only one entity of set 1. One-to-one cardinality is the subset of one-to-many cardinality. It can be represented by one-to-many. For example, in a hospital, there can be various compounders, so the relationship between the hospital and compounders can be mapped through one-to-many cardinality. Many-to-many cardinalities. In many cardinalities mapping, there can be one or more than one entity that can associate with one or more than one entity of set 2. In the same way, from the end of set 2, one or more than one entity can make a relation with one or more than one entity of set 1. It is represented by many to many or many to many, many to one, or one to many. One to one cardinality, one to many cardinality, and many to one cardinality is the subset of the many to many cardinalities. For example, in a college, multiple students can work on a single project, and single student can also work on multiple projects. So the relationship between the project and the student can be represented by many to many cardinalities. Therefore, second example, you look one student learn many subjects, and one teacher teaches many students. Many students learn from one teacher, and many teachers learn teaches for one student. Mm, no, uh, try again. One student teaches to teach. One student learn multiple teachers or multiple courses. This is example is one to many. Many to one is multiple courses are learned from students. Multiple courses learned from students. This is example is many to one. Student is specific learn from one course. This is example of one to one. Appropriate mapping cardinality. Evidently, the real-world context in which the relation set is modeled determines the appropriate mapping cardinality for a specific relation set. We can combine relational tables with many involved table if the cardinality is one to many or many to one. One entity can be combined with a relation table if it has a one-to-one relationship and total participation, and two entities can be combined with their relation to from a single table if both of them have total participation. We cannot mix any two table if the cardinality is many to many. Next point is keys. Keys play an important role in the relational database. It is used to uniquely identify any records or row of data from the table. It is also used to establish and identify relationship between tables. For example, ID is used as a key in the students table because it is unique for each. In the person table, passport number, license number, SSN are keys since they are unique for each person. Types of key. First is primary key. It is the first key used to identify one and only one instance of an entity uniquely. An entity can contain multiple keys as we saw in the person table. The key which is most suitable from those lists become a primary key. In the employee table, ID can be the primary key since it is unique for each employee in the employee table. We can even select license number and passport number as primary keys since they are also unique. For each entity, the primary key selection is based on requirements and developers. Second is candidate key. A candidate key is an attribute or set of attributes that can uniquely identify a tuple. Except for the primary key, the remaining attributes are considered a candidate key. The candidate keys are as strong as the primary key. For example, in the employee table, ID is the best suited for the primary key. The rest of the attributes like SSN, passport number, license number, etc. are considered as a candidate key. Third is super key. Super key is an attribute set that can uniquely identify the tuple. A super key is the superset of a candidate key. For example, foreign key. Foreign key are the column of the table used to point to the primary key of another table. Every employee works in a specific department in a company. An employee and department are two different entities. So we can't store the department's information in the employee table. That's why we link these two tables through the primary key of one table. We add the primary key of the department table. Department ID is a new attribute in the employee table. Employee table department ID is the foreign key and both the tables are related. Fifth is alternate key. There are many, maybe one or more attributes or a combination of attributes that uniquely identify each tuple in a relation. These attributes or combinations of the attributes are called the candidate key. One key is chosen as the primary key from this candidate key, and the remaining candidate key, if it exists, in termed the alternate key. In other words, the total number of the alternate keys is the total number of candidate keys means minus the primary key. The alternate key may or may not exist. If there is only one candidate key in a relation, it does not have an alternate key. For example, employee relation has two attributes, employee ID and PAN card number. Then, that act as candidate keys in this relation. Employee ID is chosen as the primary key, so the other candidate key, PAN card number, acts as the alternate key. Composite key. Sixth is composite key. Whenever a primary key consists of more than one attribute, it is known as a composite key. This key is also known as concatenated key. For example, in employee relations, we assume that employees can be assigned multiple roles and an employee may work on multiple projects simultaneously. So, the primary key will be composed of all three attributes, namely employee ID, employee role, and project ID, in combination. So, these attributes act as a composite key since the primary key comprises more than one attribute. Seventh is artificial key. The key created using arbitrarily assigned data are known as artificial keys. These keys are created when a primary key is large and complex and has no relationship with many other relations. The data values of the artificial keys are usually numbered in a serial order. For example, the primary key, which is composed of employee ID, employee role, and project ID, is large in employee relations. So it would be better to add a new virtual attribute to identify each tuple in the relation uniquely. Next topic is DBMS generalization. Generalization is like a bottom-up approach in which two or more entities of lower level combine to form a higher level entity if they have some attribute in common. In generalization, an entity of a higher level can also combine with the entity of the lower level of form a further higher level entity. Generalization is more like subclass and superclass system, but the only difference is the approach. Generalization uses the bottom-up approach. In generalization, entities are combined to form a more generalized entity. Therefore, subclasses are combined to make a superclass. For example, faculty and student entity can be generalized and create a higher level entity person. DBMS specialization. Specialization is a top-down approach and it is opposite to generalization. In specialization, one higher level entity can be broken down into two lower level entities. Specialization is used to identify the subset of an entity set that shares some distinguished characteristics. For example, in an employee management system, employee entity can be specialized as tester or developer based on what role that way in the company. Database aggregation. In aggregation, the relationship between two entities is treated as a single entity. In aggregation, relationship with its corresponding entities is aggregated into a higher level entity. For example, center entity offers the course entity act as a single entity in the relationship, which is in a relationship with another entity visited in the real world. If a visitor visits a coaching center, then he will never inquire about the course only. or just about the center instead. We will ask the inquiry about both. Next level is DBMS convert ER into table. Reduction of ER diamond to table. The database can be represented using the notation, and this notation can be reduced to a collection of tables. In the database, every entity set or relationship set can be represented in tabular form. The ER diagram is given below. And then some points are there. Entity type become a table. In the given ER diagram, lecture, student, subject, and course forms individual tables. All single valued attribute become a column for the table. In the student entity, student name, student ID form the column of student table. Similarly, course name and course ID form the column of course table, and so on. A key attribute of the entity type represented by the primary key. In the given ER diagram, course ID, student ID, subject ID, and lecture ID are the key attribute of the entity. The multi-valued attribute is represented by a separate table. In this student table, hobby is a multi-valued attribute, so it is not possible to represent multiple values in a single column of student table. Hence, we create a table hobby with column name, student ID, and hobby. Using both the column, we create a composite key. Composite attribute represented by component. In the given ER diagram, student address is a composite attribute. It contains city, pin, door, street, and state. In the student table, this attribute can merge as an individual column. Derived attributes are not considered in the table. In the student table, as in the derived attribute, it can be calculated at any point of time by calculating the difference between current date and date of birth. Using these rules, you can convert the ER diagram to tables and columns and assign the mapping between the tables. Table structure for the given ER diagram is as below. DBMS relationship of higher degree. Relationship of higher degree is the degree of relationship can be defined as the number of occurrence in one entity that is associated with the number of occurrence in another entity. There is the 3 degree of relationship. First is 1 to 1, means 1 is to 1. Second is 1 to many, means 1 is to many. Third is many to many, means m is to m. 1 to 1 means in a 1 to 1 relationship, one occurrence of an entity relates to only one occurrence in another entity. A 1 to 1 relationship rarely exists in practice. For example, if an employee is allocated a company car, then that car can only be driven by that employee. Therefore, employee and company car have a 1 to 1 relationship. Employees is assigned to company car. Second is 1 to many. In a 1 to many relationship, one occurrence in an entity relates to many occurrences in another entity. For example, an employee works in a one department, but the department has many employees, therefore department and employee have a one to many relationship. Third is many to many. In a many to many relationship, many occurrence in an entity relates to many occurrence in another entity. Same as a one to one relationship, the many to many relationship rarely exists in practice. For example, at the same time, an employee can work on several projects and a project has a team of many employees. Therefore, employee and project have a many to many relationship. Next topic is DBMS relational model concept. Relational model can represent as a table with column and row. Each row is known as a tuple. Each table of the column has a name of attribute, domain. It contains a set of atomic values that an attribute can take. Attribute. It contains the name of a column in a particular table. Each attribute AI must have a domain, DOM. Relational instance. In the relational database management system, the relational instance is represented by a finite set of tuples. Relational instances do not have duplicate tuples. Relational schema. A schema A relational scheme contains the name of the relation and name of all columns of attributes. Relational key. In the relational key, each row has one or more attributes. It can identify the row in the relational uniquely. In the given table, name, roll number, phone number, address, and age are the attributes. The instance of schema student has 5 tuples. Properties of relations. Name of the relation is distinct from all the other relations. Other relations. Each relation cell contains exactly one atomic value. Each attribute contains a distinct name. Attribute domain has no significant. Tuple has no duplicate value. Order of tuple can have a different sequences. Next point, DBMS relational algebra. Relational algebra is the procedural query language. It gives a step-by-step process to obtain the result of the query. It uses operators to perform queries. Select operations. The select operation selects tuples that satisfy a given predict. It is denoted by sigma, where sigma is used for selection prediction, R is used for relation, P is used for as the propositional logic formula, which may use connectors like and or and not. These relational can use as relational operators like is equal to, not is equal to, greater than is equal to, less than, greater than, less than is equal to. For example, loan relation, branch name and loan number and amount. Input sigma branch name is equal to period loan. Output branch name, loan number and amount. Project operation. This operation shows the list of those attributes that we wish to appear in the result. The rest of the attributes are eliminated from the table. It is denoted by A1, A2, An, where A1, A2, A3 is used as an attribute name of relation R. Third is union operation. Suppose there are two tuples R and S. The union operation contains all the tuples that are either in R or S or both in R and S. It eliminates the duplicate tuples. It is denoted by U. Notation R union S. A union operation must hold the following condition. R and S must have the attribute of the same number. Duplicate tuples are eliminated automatically. Set intersection. Suppose there are two tuples R and S. The set intersection operation contains all tuples that are in both R and S. It is denoted by intersection. Fifth is set differences. Suppose there are two tuples R and S. The set intersection operation contains all tuples that are in R but not in S. It is denoted by intersection minus. Cartesian product. The Cartesian product is used to combine each row in one table with each row in the other table. It is also known as a cross product. It is denoted by X. Rename operation. The rename operation is used to rename the output relation. It is denoted by RHO, row. DBMS join operations. Join operation. A join operation combines related tuples from different relations if and only if a given join condition is satisfied. It is denoted by. And then types of join operation. Join operation is natural join, outer join and equivalent join. Outer join is third topic is left outer, right outer and full outer join. First is natural join. A natural join is the set of tuples of all combinations in R and S that are equal on their common attribute names. It is denoted by sigma. Outer join. The outer join is an extension of the join operation. It is used to deal with missing information. An outer join is basically of three types. First is left outer join. Second is right outer join. Third is full outer join. First is left outer join means left outer join contains the set of tuples of all combinations in R and S that are equal on their common attribute names. In the left outer join, tuples in R have no matching tuples in S. It is denoted by right outer join. Right outer join contains the set of tuples of all combinations in R and S that are equal on their common attribute names. In right outer join, tuples in S have no matching tuple in R. It is denoted by C. Full outer join. Full outer join is like a left or right join except that it contains all row from both tables in full outer join. Tuple in R that have no matching tuple in S and tuple in S that have no matching tuples in R. In their common attribute name, it is denoted by third is equijoin. It is also known as an inner join. It is the most common join. It is based on match data as per the quality condition. The equijoin uses the comparison operator. Next point is DBMS integrity constraints. Integrity constraints means integrity constraints are a set of rules. It is used to maintain the quality of information. Integrity constraints ensure that the data insertion, updating, and other processes have to be performed in such a way that data integrity is not affected. Thus, integrity constraints is used to guard against accidental damage to the database. Types of integrity constraints. First is domain, second is entity, third is referential, and fourth is key. First is domain constraint. Domain constraints can be defined as the definition of a valid set of values for an attribute. The data type of domain includes string, character, integer, time, date, currency, etc. The value of the attribute must be available in the corresponding domain. Second is entity integrity constraints. The entity integrity constraint states that primary key value can't be null. This is because the primary key value is used to identify individual rows in relation, and if the primary key has a null value, then we can't identify those rows. A table can contain a null value other than the primary key field. Referential integrity constraints. A referential integrity constraint is specified between two tables. In the referential integrity constraint is if a foreign key in table 1 refers to the primary key of table 2, then every value of the foreign key in table 1 must be null or be available in table 2. Fourth is key constraints. Keys are the entity sets that is used to identify an entity within its entity set uniquely. An entity set can have multiple keys, but out of which one key will be the primary key. A primary key can contain a unique and null value in the relational table. DBMS relational calculus. Relational calculus. There is an alternate way of formulating queries known as relational calculus. Relational calculus is a non-procedural query language. In the non-procedural query language, the user is concerned with the details of how to obtain the end results. The result calculus tells what to do but never explains how to do. Most commercial relational languages are based on aspects of relational calculus including SQL, QB, and QQL. Why it is called relational calculus? It is used to it is based on predicted calculus. A name derives from branch of symbolic languages. A predict is a truth value function with arguments. On substituting values for the arguments, the function result in an expression called a proposition. It can be either true or false. It is a tailored version of a subset of the predicted calculus to communication with the relational database. Many of the calculus expression involves the use of quantifier. There are two types of quantifiers. Universal quantifiers. The universal quantifiers denoted by A is read as for all, which means that is a given set of tuples. Exactly all tuples satisfy a given condition. Existential quantifier. The existential quantifier denoted by E is read as for all, which means that in a given set tuple of it, at least one occurrence whose value satisfy a given condition. A tuple variable t is bound if it is quantified, which means that if it appears in any occurrence, a variable that is not bound is said to be free. Free and bound variable may be compared with global and local variable for programming language. Types of relation calculus. Tuple relational calculus. It is non-procedural query language which is based on finding a number of tuple variable, also known as range variable for which predict holds true. It describes the number desired information without giving the specific procedure for obtaining that information. The tuple relation calculus is specified to select the tuple in a relation. In TRC filtering, variable use is the tuple of relation. The result of the relation can have one or more tuples. Notation: a query in the tuple relation calculus is expressed as follows. Following notation: T is the resulting tuples. Condition used to fetch T. Output: this query selects the tuple from the author relation. It returns a tuple with name from other author who has written an article on database. TRC can be quantified. In TRC, we can use extensional and universal quantifiers. For example, domain relational calculus. The second form of relation is known as domain relational calculus. In domain relational calculus, filtering variable uses the domain of attributes. Domain relational calculus uses the same operators as tuple calculus uses logical conventions. It uses extensional and universal quantifier to bind the variable. The QBE or query by example is a query language related to domain relational calculus. This query will yield the article, page, and subject from the relational Java point where the subject is a database. Thank you.